Hi, my name is Ariel Mendelman, and in this presentation, I'm going to show how I'm using data geometry in order to improve three main tasks in machine learning: representation learning, prediction, and data generation. So let's start. We'll start with representation learning. In many problems, we want a low-dimensional representation of high-dimensional data that is still meaningful. Here, we reduce 3D data to 2D while keeping points of the same color close, so classification still works well in 2D. In real applications, data is often much higher dimensional. For example, with images, each sample has as many dimensions as pixels. In this toy example, our goal is to predict Superman's rotation angle from each image. Using the standard diffusion maps algorithm, we embed the images in 2D and color them by Superman's rotation angle. But the data is confusing due to the Spider-Man and Flash figures that are irrelevant to the task. And as you can see, the learned representation is not aligned with the task and is ineffective. In my research, I show that if we have some labels, we can extract the common geometry between data and labels and learn a representation that is much more task-effective. As you can see on the left, the representation learned using our method is much more effective. This work was published at ICLR 2025, one of the top conferences in AI. Next, I use data geometry for improving prediction. Beyond images and text, graphs are an important data modality that can be analyzed with machine learning, especially with graph neural networks. For example, we can treat Netflix users and movies as nodes in a graph and predict which movies a specific user will like. In my second work, I use similar common geometry idea for graph rewiring. I modify the graph structure itself to help a graph neural network make better predictions. I prove mathematically that my rewiring method increases graph homophily, meaning that nodes are more likely to connect to other nodes of the same class, a property that is known and that we further analyze to be beneficial for graph neural networks. This work is currently under review for ICLR 2026. Finally, I turn to data generation. Generative models are used today to generate different types of data, for example, images, as you can see here. I'm currently working on modifying the generation process in existing generative models so that it respects the underlying data geometry. For example, in this simple case, I want the model to follow the spherical geometry of the data instead of moving along naive straight lines. This makes the intermediate samples stay on the data manifold and leads to a better final sample. Thank you very much for listening.